Solubility product is the equilibrium reactions around sparingly soluble salts. Many ionic compounds are sparingly soluble. Barium sulfate is a really good example. So barium sulfate, if we look up in the data books, it has a solubility of 1.05 times 10 to the minus 5 mole per decimeter cubed. What does that actually mean? Well, it means that if I weigh out 1.05 times 10 to the minus 5 moles, well, we don't work in moles, we work in grams. So I can multiply that by the molar mass, and the molar mass of barium sulfate is 233.4 grams per mole. When I do that, it comes to 0.00245 grams. So if I weigh out 0.00245 grams of barium sulfate, that's not a lot, and I dissolve it in an entire decimeter cubed, that's 1,000 centimeters cubed of water, I will have a saturated solution. I've got a picture of a saturated solution here, and in it we have an equilibrium between our solid barium sulfate, and that is an equilibrium with barium ions and sulfate ions. And remember, this is a dynamic equilibrium. So we have got solute dissolving and ions precipitating out at the same rate when we are at equilibrium. The equilibrium constant for this equilibrium, for a sparingly soluble salt, is called the solubility product, and it is given the symbol Ksp, and we write it in the way that we write any of these expressions. So it's the barium ion concentration times the sulfate ion concentration, products over reactants, and we've got barium sulfate solid. Now, of course, we can't have a concentration of a solid, so we can ignore that. So the solubility product is essentially the product of the concentration of the ions in solution. Now, solubility product, this equilibrium only applies to sparingly soluble salts, in which we have very few ions in solution. As a result, we can assume that they're electrically neutral. The barium ions and the sulfate ions are so dilute that they're not interfering with each other in any way. This isn't actually the case for more soluble salts, sodium chloride, for example. If I've got sodium ions and chloride ions in solution, because sodium chloride is really very soluble, I have a large number of ions and they interact with each other. So their effective concentration is not the same as their actual concentration. We can calculate a value for the solubility product for Ksp in a very straightforward manner, so long as we know the solubility of our solid. Barium sulfate dissolves to form barium ions and sulfate ions in a 1-to-1 ratio. I know the solubility of barium sulfate, it's 1.05 times 10 to the minus 5 moles per decimeter cubed. So 1-to-1 ratio, concentration of the barium ions in solution at equilibrium is 1.05 times 10 to the minus 5. As is the concentration of the sulfate ions, as I said, 1-to-1 ratio. And when you plug that into your calculator, that comes out at 1.10 times 10 to the minus 10. And the units in this case, mole squared dm to the minus 6. So solubility product of barium sulfate is very, very small, and the numbers are always going to be very, very small because we're always dealing with sparingly soluble salts. So what does this number tell us? What does the solubility product for a sparingly soluble salt tell us? Well, if I mixed two solutions, one containing, that's a really bad beaker, isn't it? One containing barium ions and one containing sulfate ions. So for example, it might be barium nitrate in solution, and let's go with sodium sulfate. Those are both soluble salts. If I mix those two together, then we would expect barium sulfate to precipitate out if the product of the ion concentrations of the barium and the sulfate exceeded KSP. If it was less than KSP, then we wouldn't have a saturated solution, no equilibrium present, and we wouldn't see the solid precipitate out. Finally, let's look at an exam style question. Calculate the solubility product of chromium hydroxide, given that it has a solubility of 1.39 times 10 to the minus 8 mole per decimeter cubed. You always need an equation for this equilibrium because we need to know the ratios. Chromium hydroxide is in a 1-to-1 ratio with chromium ions and a 1-to-3 ratio with hydroxide ions. So KSP, if we write our expression, is the chromium ion. Remember, always include state symbols. Multiplied by the hydroxide ion concentration to the power of 3, because we raise it to the power of 3 because we got 3 hydroxide ions in our stoichiometric equation. We know that chromium hydroxide to chromium ions is a 1-to-1 ratio, so the concentration of chromium ions is 1.39 times 10 to the minus 8. The concentration of hydroxide ions is going to be 3 times that. It's a 1-to-3 ratio. So that would be 4.17 times 10 to the minus 8. Then we can multiply that by the cube of that. So yeah, it does seem like we're kind of multiplying up many times, but pay attention to the method always. And the solubility product comes out to be 1.01 times 10 to the minus 30. In this case, mole 4, dm to the minus 12, that should say. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.